Alright, so we're working in section 3.6 and we're looking at a new method for finding a non-homogeneous, or the particular solution for the non-homogeneous equation. And this is different than the previous section in that we don't have constants up here anymore. We have generic A, B, and C, although they could be, or sorry, we don't have A, B, and C. We have P of t and Q of t. Okay, so these could be very complicated functions. We're going to be given y1 and y2, and we're going to try to find y sub p, and I'm going to go ahead and write down the method here. The ansatz that we're going to use is that y sub p is u1 y1 plus u2 y2. So if this is our ansatz, by the way, you'll notice a similarity to this ansatz versus the reduction of order. So in reduction of order, you wouldn't have this half, right? But we would say that y2 was equal to v of t times y1 of t. And so this is very similar to that. Okay, so but in this case we're looking for the full homogeneous solution to this differential equation, and our ansatz is u1 y1 plus u2 y2. Good. So what do you do with the ansatz? Well, you're going to plug it into the differential equation, but what we're going to see is that u1 and u2 happen to satisfy a couple of equations, this system of equations. So notice if I have y1 and y2, then the only unknowns in this system of equations are the u1 prime and the u2 prime, which I could solve using Cramer's rule. Okay, and so when you use Cramer's rule, what happens is the denominators are going to be Wronskians, the Wronskian of y1 and y2. And so when you compute the determinant, right, this is going to be y2 times, or minus y2 times g of t, and this one's going to be positive y1 times g of t. Okay, and this method right here is called the variation of parameters. This technique here is called variation of parameters. Good. So let's prove the variation of parameters. The steps for the algorithm is we're going to first differentiate our ansatz to get yp prime. We're going to assume something extra, and this assumption is here because we have an extra condition that we need to specify in order to make u1 and u2 be well defined, I guess I could say. Okay, then we'll differentiate that again to get the second derivative, and then finally we'll plug everything into the differential equation and see if we can solve for u1 and u2. Okay, so again we're just differentiating our particular solution like usual, substitute it into the differential equation. Good. So let's go ahead and differentiate. So I'm using the product rule here. So these first two are the product rule for u1 y1. The second two are u2 y2. And remember what we said, our assumption is going to be that this actually forms our first constraint, that u1 y1, or u1 prime y1 plus u2 prime y2 is equal to 0. Okay, so that actually simplifies this function. So the first and the third terms go away, and you're just left with u1 y1 prime plus u2 y2 prime. That makes it a lot easier, right, to differentiate for the second derivative. And so if we differentiate it there, we'll get this expression. And again, the first two are just the product rule for this term. Second two are the product rule for this term. Okay, now we want to substitute this and this into the differential equation and see what we get. Good. And so I'm just writing it in tabular form here. This is my second derivative. And I've gone ahead and multiplied my first derivative times p. And notice that I'm putting it in order in kind of a suggestive way here. Right, and so then I've got the q times the original function here, so that's down here. And do you see why I wrote it this way? You might notice here and here. Yeah, those two expressions are equal to 0. And why is that? Because y1 and y2 solve the homogeneous equation. Very good. And so therefore, the second constraint is given right here. And so now we have a system of equations, two unknowns and two equations and two unknowns. How are we going to solve that system of equations? Using Cramer's rule. Good. And so Our conclusion is variation of parameters is a method to obtain a particular solution. I shouldn't have just read this to you. You can read it yourself. For the second order differential equation. And so the formula is right. Once you're given the y1 and y2, we can figure out y sub p by using the ansatz y sub p equals u1 y1 plus u2 y2. And then we need to, so y1 and y2 are known, u1 and u2 are unknown, and from our formula that we just had, we know that the solutions can be gotten from these two equations where we use Cramer's rule to solve. Good? All right. And so now, of course, we want to actually go through an example. So here's an example, 4y double prime minus 4y prime minus 8y equals 8e to the minus t. Notice, by the way, that if I were just looking at this differential equation and I just said, find the solution to this, I would not use variation of parameters, right? I would use the method of undetermined coefficients. But this is just an example of how you would use variation of parameters if you wanted to. Okay, and so the very first thing you want to do is to write this in standard form. Just get used to that, because otherwise you're going to be sure it's really easy to mess that up, because we don't have to get standard form, right, to solve for the homogeneous part of the solution. So divide by 4 first, and we get the standard form of our differential equation. And now, see, this is the g of t that you want to use. You don't want to use 8 times e to the minus t. You'll get the wrong answer. Okay, and now that we've got our differential equation, let's see, does this factor r squared minus r minus 2? Is that a minus 2 plus 1? So that'd be r equals 1 and negative 2. R equals 2 and negative 1. Yep. Good. So there's y1 and y2 for our formula, right? So now we assume that y sub p is equal to u1 times y1 plus u2 times y2. We have our g of t, and so now we can plug everything into the formula. We need the Wronskian, so let's go ahead and compute that. E to the 2t times e to the minus t is e to the t, so that's going to be a minus e to the t there. And then we'll have a minus 2 e to the t there, so we get minus 3 e to the t for the Wronskian. That's the denominator of our system, right? Good. And so u1 prime then is going to be, this is our right hand side, right? This is Cramer's rule, and this is our y2 prime. Okay, and so this is our Wronskian, and so we just compute that, and things work out nicely for us. We just get 2/3 e to the minus 3t, and that is u1 prime. That's easy to find u1 from, just integrate. Good. Similarly, u2 prime is found from Cramer's rule. So you see here, this is y1 and y1 prime, and this is the right hand side, right? This column just came down here. Good. And now when you simplify, you just get minus 2/3, and so that u sub 2 is going to be minus 2/3 t. Now we have u1 and u2. We can figure out what our y sub p is. u1 y1 plus u2 y2. Okay, so that's just going to be our u1 times y1 plus u2 times y2. And if you simplify that, you get this expression down here. Now this is more than I need. I don't need this entire thing. Do you see that this minus 2/9 e to the minus t was actually, where is it? Where's our homogeneous part? There's the homogeneous part. That's actually part of the homogeneous solution. So therefore we don't really need that. We don't need it in y sub p, because if you plug this part of the solution in, you just get 0 from the differential equation. Okay, so therefore we're just going to keep this piece as y sub p. Okay, and so y sub p will be minus 2/3 t e to the minus t. Good. Put it all together. I might say when we're integrating u1 and u2, do we need to include the constant? What happens if we do? Well, notice that when you're computing y sub p then, right, if you have that extra constant in there, do you see what's going to happen? You're just going to be including c1 y1 plus c2 y2 in the particular part of the solution, but you don't need to, because these things evaluate to 0 using the differential equation, right? And so you don't need the constants when integrating u1 and u2. Good. All right. So now our second example, I think I might pause here because this is kind of an extended example and we're already at 10 minutes. Okay, so the next video we'll just do one more example and then we'll also do a summary.